Okay, hello everyone. My name is Aaron Stannard, and I'm the CEO of a company called MarkedUp. We're an early stage technology company, and we do in-app analytics for native software, right now primarily on the Windows platform, although we're adding support for other technologies too. I'm ex-Microsoft, and so are a number of the other people on our team. So, there we go. So before I really get into the substance of our talk, which is really about sort of building a real-time analytics cluster using Cassandra from the ground up, I want to talk a little bit about what our company does. So we help developers learn 3 types of things about their software after it gets deployed to the marketplace and is running on their end users' computers. The first is we go and help them learn like who's their audience, who's actually using the app every day, what types of devices do they run, how often do they come back and use the app over and over again. These are things you sort of need to get a sense for who your audience is and what you should be testing your product on in terms of QA and hardware and so forth. And so that's the first thing that we do. The second is we capture diagnostic information about our customers' apps. So crashes, exceptions, performance monitoring, and so forth. We're trying to help the operations and development teams understand how their app is actually, how well it's running on other people's computers. And the last and most important thing we do is we help our customers make more money. We help them identify, which customers have intention to buy versus which ones don't. So, we work with some pretty big video game companies, and some of them will say, oh, well, I think, American kids between the ages of 25 and 18 will be great users for this app. And we'll say, actually, Japanese 13-year-old women, probably who you should be targeting for this application. So we'll have, we basically have the ability to back that up with data about our sort of worldwide install base for Windows 8. That's what we do. And you probably heard a number of talks today about companies like Netflix and Kissmetrics and others who are dealing with petabyte scale and all these sort of crazy sort of scalability problems. We're not there yet. We're a very early stage technology company. We deal with millions of data points a day. But the types of problems I'm going to be talking about today are for people who are looking to build their first sort of real-time analytics cluster where you need to be able to measure some things in real time, want to be able to integrate Hive and Solar into it, and so forth. So I'm going to sort of work from the bottom up and help give you a picture of how to get started with Cassandra and DataStax Enterprise in production. So it all begins with one question. Oh, this is our product. It all begins with one question. Do you really need real-time analytics? I'm going to shatter your world right now and tell you that real-time analytics is a developer buzzword. It's just like, it's the engineering equivalent of big data. You don't need real-time analytics for everything, and in fact, there's a lot of use cases where it's a bad thing, where you shouldn't conflate your operational metrics you need to keep something running with strategic metrics you need to decide how to do something in the future. So let me give you an example. The way we break down analytics is really into 3 families. We have real-time, retrospective, and a third type that's not on the board here called predictive analytics, which is what's going to happen in the future. Real-time analytics is designed to help you keep a pulse on things that are happening as they happen. And the only analytics that really need to be real-time are ones that you can respond to in real time. So all of you have probably had, if you're a developer, error monitoring software at some point in your lives, or keeping tabs on the health of your servers in production. That's the perfect use case for real-time analytics, because if something goes down, you have a business obligation to respond to it in real time and try to fix the problem as it happens. Likewise, if you're a stock trader, you need to get pricing information in real time about stocks, so you can make business decisions based off those. These are examples of types of things you can respond to as they happen. But what about instances where you need retrospective or historical data? So imagine you're a scientist and you're studying changes in solar flare intensity over the past 10 years, trying to determine if there's some changes in the sort of sun's behavior. You don't want that in real time because you don't want to have a report every day when there's a fluctuation or an outlier telling everyone that we're all going to die from UV exposure one day, then the next, oh, our bad, we had a problem with the server. Silly us. It's much more important to actually take a statistical sample over a period of days, months, or even years and produce a consistent result using a tool like Hadoop for something like that. So what we're going to talk about today is how to build an analytics system that leverages both of these types of techniques to really drive valuable business insights for your company internally or for your customers if you're building an external facing product. I'm really going to try to help you think about it from both a technology and a business point of view. So the point being is that real-time analytics isn't inherently better than analytics that aren't real-time. It's just different types of metrics that can and should be responded to in real time. So here's how we look at real-time analytics at MarkedUp. So I talked a little bit about what our product did. So most of our metrics are operational. These are things like install rates for applications, number of people who've used it every day, error rates, custom events, and so forth. These are things our customers can respond to in real time. So one thing we can do that like the Windows Store doesn't do very well for our customers is we let them know exactly when their app gets approved from the store, how many people are installing it in different countries around the world. Because what if you're trying to time PR and marketing around that, and you want to be able to hit the date exactly right? Well, that's something that we can do, and our customers can respond to that. Likewise, what happens if your error rate suddenly spikes up in your application? A lot of our developers are Microsoft sort of loyal developers, and about, I think it was 6 months ago, Windows Azure had an SSL issue with storage. So we noticed a 15% climb in the error rate across all of our applications when this happened. We didn't know what was going on. And it turns out that a lot of our apps depended on Azure for storing images and other static content that they pulled out. So had it been their own backend, they could have done something about it. But since they were talking to Azure directly, they were kind of screwed for the most part. So these are the types of analytics that we measure and report on in real time as they happen. Otherwise, we have some metrics that are retrospective, like user retention. How long do you retain users after you've gotten them to install your app? That's something where we need to measure multiple distinct events over a window of 30, 60, or even 180 days. So we do that with Hive and Hadoop after we gather all this raw origin data inside Cassandra. So let's talk about how we actually build a system that is capable of doing both of these really well, retrospective and real-time analytics. So we use DataStax Enterprise real heavily. Even though we're an early stage technology company, we only have 5 full-time people at the moment, and I went full-time on it in August. We've been able to partner with DataStax, and they've been a really great business partner for us. So we've had a tremendous experience with their products. We actually had to migrate onto Cassandra in an emergency. We prototyped our product on top of another NoSQL database called RavenDB, which I don't know if you've heard of. Think of it as like MongoDB, but all with Lucene.NET under the hood and a bunch of really cool built-in indexing capabilities. It was a great tool for prototyping, but as soon as Thanksgiving rolled around, we went live with 2 of the largest apps in the Windows Store, including like a number 1 or 2 video game, and it completely pegged our servers to a point where reports are running behind by 3 or 4 days. Reports that are supposed to be in real time, mind you. So we had a major problem on our hands. So it took us about 2 months to move everything onto Cassandra off of Raven, and we were able to do that because of DataStax specifically. So I can't say enough good things about their technology and what they're able to do for us. So getting down to nuts and bolts, let's talk about what do you need to do to get a basic analytics cluster up and running on Amazon EC2, which is, if you're a small team or if you're doing this with your own resources, this is probably the first natural place for you to go and look. It's how to do it on Amazon Web Services. So from a VM perspective, DataStax actually has a really convenient what's called auto clustering, AMI, for DataStax Enterprise. And what this will do is you bring up 4 or 5 or 6 nodes, and it'll go and negotiate, okay, this node runs Ops Center, this node has Hive, this node has Solar, and it'll go and set up all the configuration settings for you. It'll automatically form the ring. It takes a lot of the sysadmin work that would probably take you, a week or 2 on your own, just done for you auto-magically. So that's what I recommend, is using your sort of base AMI when you're just getting started. Now, there are some limitations to be aware of. If you need to do multiple availability zone or multiple region replication on Amazon, you're not going to be able to get that out of the box with their built-in AMI, so you'll have to roll your own eventually. But for just getting up and running, this takes like 30 minutes to set up. So it's really convenient. In terms of your VMs themselves, we highly recommend using Ubuntu 12.04 LTS as your sort of operating system, which that'll usually ship by default in the Amazon AMI. We recommend using 6 large instances. 4 of your nodes will be pure Cassandra nodes where there's no Hive, no Solar, no Hadoop, none of that stuff running on them. And then 1 node that's dedicated to just Hive and Solar, and then 1 node just dedicated to Hive and Hadoop, and then 1 for Solar. This is a really good basic cluster setup. And the way you should design your application around this is have it talk to the 4 writable nodes at any given time, and then let Hive and Solar sort of sit off on the side and do their own thing. And then from actually setting up your first key space in Cassandra, these are a lot of the settings that we use in production today. And with all due credit to Jay Patel from eBay, I stole a lot of this from his talk last year when I was trying to figure out how to set up my cluster for the first time. So for consistency, we recommend setting the write to 1. Just hand it off to the server and bail if you know that your write load is going to be really high. Set it to 2, so that way at least 2 servers agree on what this value should be when you're reading out of Cassandra. And then for your replication factor, we always recommend going with a replication factor of 3 for Cassandra. And the reason for that is if you have a cluster with or a ring with at least 4 servers in it, you can have up to 2 of them go down and still be able to maintain 100% of your data. So it allows you to survive multiple node failures on a small cluster. So 3 is a good replication factor to have. And then if you're using the network topology placement strategy, what DataStax Enterprise will allow you to do is sort of add new analytics and Solar nodes somewhat independently of your Cassandra ring. So if you want to distribute your Hive or Hadoop workload among multiple workers, this will allow you to sort of scale that going forward. So it sort of has like mini clusters going on within your Cassandra ring, if you think about it that way. And then for partitioners, if you're using anything other than the random partitioner, you probably are way too sophisticated for this talk. Ordered partitioners are expert mode only sort of features, and I haven't actually seen very many of them in production ever. So, but they're there if you do need it. So let's go ahead and talk next about sort of how we actually work with Cassandra in production. So this is from the application's point of view, is what we're talking about here. So with analytics, the write to read ratio is going to be astronomically high. You're going to have 1,000, 10,000, maybe even 100,000 writes for every read. So what we tend to do in our setup is we take advantage of the fact that Cassandra is, generally speaking, much more performant at handling writes than it is at handling lots of reads. So we denormalize our data heavily at the API level before we write to Cassandra, and we use a batch mutation to go and change Cassandra all at once. So here we have like 3 column families. We have this logs column family on the bottom, which is, think of that as like origin raw data that we're going to process through Hadoop a little bit later. That's the raw object as it's being sent to the API. And then we have some counters which just roll up daily totals for each of these. So we have one counter that shows the total number of logs for each application on our platform, and then another set of counters that show the number of logs at different log levels that we support. So how many of these logs represent fatal errors, how many represent just normal trace versus debug info, that sort of thing. Just the normal sort of tracing levels. So what we do is a new log hits our API, we denormalize it and put it into a batch mutation, and that batch mutation will atomically make all these changes throughout Cassandra at once. And the difference in terms of the amount of time it takes for modifying 1 column family versus modifying 40 is actually not that much to the client. It's actually been difficult for us to measure the difference in speed. So really, you're not really giving anything up by using batch mutations. So that's the strategy that we strongly recommend is sort of when you're just getting started. Now for read strategy, interesting story. So most of our developers are all .NET guys, which means SQL's like in their blood. I actually had to go in and try to disable the SQL 3 driver when we were first getting started because they kept wanting to gravitate towards their sort of SQL habits when we were first getting used to Cassandra. This is before we went live with it in production. So what we do, and what I strongly recommend for working with time series data, is use the Thrift APIs. You can use a tool that's called a slice range to go and, so let's say we have this column family here where we're counting the total number of logs by level every day. So how many crashes versus errors versus traces did we have in this 30-day window for this application? What we can do is is there a laser pointer on here? No. Actually, I don't know what this button does. Maybe I shouldn't touch it. Oh yeah, well, that did something. Long story short, we have different keys here for each of the different log levels, and what we do with the slice range is we're able to go and say, okay, I want to grab everything starting at date 1. Let's say date 1 was 30 days ago, and grab everything up to date N, which is today. And you basically say, all right, Cassandra, take from this column until this one. And because we have dates as our column names, and columns are physically sorted and stored next to each other in Cassandra, it'll grab that whole chunk at once for each row and return it in one blob. And then from there, we'll go and do stuff like check to make sure that all the dates are there's a value for each date, and if there isn't, we'll go and substitute a 0 for it on the chart. That way it doesn't look weird. And this is the sort of read strategy we use, and this is very fast. So now we're going to talk a little bit about how to design a schema to support this and what are some of the principles and rules you need to think about. So in terms of a schema strategy, things that I recommend doing, one is make sure that your row keys are always predictable, i.e. you shouldn't need a separate lookup table to figure out which rows you need to fetch in order to satisfy a read query when you're trying to get some data out of Cassandra. Design your keys in a way where you can always predict what the values are going to be. And I'll show you a little bit more about that on the next slide. Then on top of that, make sure you're leveraging the physical sortability of columns. Particularly if you're managing time series data, this will make your life so much easier. You'll be able to look up anything in constant time, essentially, in terms of, I want to start from this column and go to this one, where column A is your start date and column B is your end date. And it'll grab everything in between. So if you leverage that property, it makes it really easy to manage time series data inside your Cassandra cluster. And one other sort of gotcha, we found this out the hard way when we were just getting started with Cassandra. Make sure you use predictably sortable data types for your column names if you're managing time series data. So use long integers and use date times, use ints. Don't use things like strings or composite types because you might get unexpected results. So we were using a composite type initially, I think, for our column name, and we got burned big time by that. So we totally redesigned our schema to make sure that all the column names are always a really simple type that sorts well. And we'll talk about some of the other things on the right-hand side as we go. One recommendation I also make is that when you're just getting started with Cassandra, stick with distributed counters for your real-time analytics. As you get more sophisticated, you'll find that there are some issues with distributed counters. So for instance, there's not really any good support for retry logic on them. The counters are essentially atomic values that you can increment or decrement with individual commands. You can say increment by this much, decrement by this much. But what you can't really do is, unlike the rest of Cassandra, where you can go and overwrite a value, you can go and say, all right, I'm just going to overwrite the value of this row, and it'll just go and reset everything so it's fully idempotent. With counters, you lose that ability, that it'll get incremented again if you retry it and the operation goes through. So there are some downsides to using counters, but for the most part, they're really easy to set up and are actually pretty easy to work with. So it depends a lot on the types of data that you're measuring. I would never use counters to measure like the outcome of a financial transaction. 5 minutes left? Wow. Guess we better step on it. So for the first schema here, and I'll go ahead and leave this up for you on SlideShare so you can take a look at the notes. This is a schema that you'd use for a totally predictable sort of data structure. So in this case, daily app logs per log level. We know the ID of the app that we're looking for because that's contained in the request we get from one of our customers. And we know the different log levels that we want. So our row key is totally predictable. And we also know the date range. We know that they want everything from this date to this date. So our Cassandra column family has all the data it needs to satisfy a query sitting in a single row. So this row will grow over time, and eventually it can become a really wide row potentially if we have millions of hours worth of data on here. But there's also a naturally limiting factor to that, right? There's only X number of days or hours per year, and so you can sort of capacity plan around that really easily. The next sort of schema type that we use is what's called a bounded number of knowns, or bounded number of unknowns. So the scenario we have in this case is, let's say one of our customers wants to know the number of users by version, or in this case, the number of error logs by exception type. So we have no way of knowing what the exception types are going to be, but we know that the number of different types of exceptions will be relatively low, maybe under a dozen usually, unless you have a really bad developer, which case we probably don't want them as a customer. So you're not going to have more than 10 types of exceptions, Stack Overflow, out of memory, et cetera. So what we tend to do for this is flip the schema on its side, where we have the known properties, sort of the app ID and the error log, but we also have the date as part of the composite key here. So we'll be fetching a much larger number of rows this time around, but all of the unknown values are contained as columns. And we just say, okay, go ahead and grab at least 200 columns for each row. And then we sort of transform it back into a time series at the application level. So this is a great technique when you have a relatively small number of unknowns you have to work with, because it's simple to work with and doesn't require multiple round trips. Now, if you have a totally unbounded number of unknown things, we recommend using an index column family for that. So in this case, in our batch mutation, whenever a developer sends us a custom event, and usually they have hundreds of these, we go and keep the names of the custom events in a separate column family. We're using the null value pattern for this, where the actual value of the column is null, and the column name itself is the value that we want. So we'll take this data, and we'll go and query against an actual type 0 column family that has all of the time series data for each custom event in it. So it takes 2 different network round trips, which is the one disadvantage of this pattern, but it really limits the number of rows we have to query. Each one of these patterns I've shown you takes under 100 milliseconds for us to run in production. So in terms of the amount of time it takes the HTTP request to hit our API and for us to get a response back. So most of the time that our clients spend waiting on data is actually downloading JSON objects from our server more than anything else. So it's a really good way to curb some of the complexity here. You guys can look at this on the site. Adding Hive and Hadoop to the mix. So I want to touch on this before we end our talk. When is Hadoop necessary is a question that I found myself asking right when we were getting MarkedUp started, having not had a lot of experience with it before. And my answer on this is, when you start getting into the 100 gig data set range, Hadoop starts becoming a more and more valuable feature over time. There's sort of a minimum size of a data set you need to really get any value out of Hadoop, and 100 gigs has sort of been the threshold for us. But the other things you should think about from a requirements point of view if you need Hadoop, if consistency is really important for you, Hadoop is a great tool for the job for that. If speed isn't a requirement, Hadoop is slow. It is really slow. You're not going to get real-time results from it. It might take 30 minutes for it to go and produce a query for you, but the results will be consistent and will touch on all the data you need it to get. And the last thing is, if you have really complex query pipelines, like so for instance, counting the number of distinct items that fall under these different cohorts and et cetera, Hadoop's actually a great tool for doing that. So if you need a really good MapReduce pipeline, Hadoop's a perfect tool. So we're lazy, so we like to put Hadoop on easy mode, and we call that Hive. So DataStax Enterprise Edition has bindings for Pig and Hive. Pig scared us, so we decided just to go with Hive instead since we're all SQL developers. So Hive was developed by Facebook originally, just like Cassandra, and it was meant to be a data warehousing technology to allow some of their non-technical people to be able to go and get information about Facebook's users. So what's convenient about it is that there's actually a lot less deployment and overhead that goes into running MapReduce queries if you're using Hive or Pig instead of raw Hadoop. You don't have to deploy any code to your analytics node. And you can go and, if you want to set up a recurring Hive job, it's as easy as running a cron job that just invokes something on the command line. So it's really easy to deploy and get up and running. And to give you a sample of what the workflow looks like, let's say you have this column family, the logs column family in Cassandra. If you want to start analyzing it in Hive, what you do is you go ahead and create what's called an external table. And so I'm not going to read all the syntax on there, but that's actually the legit syntax for mapping a Cassandra column family with dynamic columns into a Hive table. So Hive tables is very much sort of a one-to-one mapping with what's in Cassandra. It has different data types, and you have to account for some translation there. But for all intents and purposes, it's pretty easy to work with. And you know what the best part is? Hive automatically fetches data back from Cassandra as it updates. That mapping is sort of perpetual, in other words. You don't have to go and run jobs to reinsert new data or anything else. It just runs and works. So, and then here's sort of what the query syntax looks like for getting data back out. As you can see, it's virtually identical to what you'd do on like the MySQL command line if you wanted to run it. So, just some final tips and tricks about Hive. We're going to have to skip the Solar part, unfortunately. I'm sorry, guys. Let you down. Don't write. So if you're reading and writing from Hive and Cassandra, make sure that only one of those 2 data sources is doing the writing. In other words, if you have a column family that's being updated by your application server and it's writing directly to a Cassandra column family, don't let Hive write to it also. Otherwise, bad things will happen. So for instance, our user retention and our average time spent in app reports, all that data gets written back to Cassandra by Hive, but they're in dedicated column families that our application never writes to under any circumstances. So we found that's the best way to sort of make sure you don't have one service overwrite the other. And then the second is, if you are trying to test Hive queries, you can use sampling. So for instance, instead of looking at the entire data set, you can look at just the past 30 days worth of data. So that allows your Hive jobs to complete in like 10 minutes instead of 2 hours, depending upon how big your data set is. So those are our sort of tips and tricks for working with it. All right, well, unfortunately, I'm not going to be able to answer this question today. But anyway, thanks for listening. And do we have time for questions? Or? Time for 3 questions. Okay. So it depends on what rollups you want. So right now, the way we do date columns in our data set is they're actually timestamps that are marshaled to the latest UTC day. You could go and do it if you wanted to, hourly or even down to the minute if you wanted, and that technique will still work. All that you have to bear in mind is when you're doing that column slice from one date to another, it will get everything in the middle potentially. So what I recommend doing is having different column families for different granularity. Have one that's a daily roll-up, one that's hourly, one that's by the minute if you need it down to that level. That way you sort of have an expectation for what the volume of data is going to be right there. Any other questions? Interesting anecdotes? Yes? That's totally not fair. The answer is use a faceted search in Solar, but how do you count 1 million distinct items in real time? And the answer is well, actually, I'm going to cheat. This. Basically, you go ahead and define a Solar index, and I'm not going to get into the syntax here, but essentially you can use faceted search, and one of the things Solar outputs is a number of records that match, and it's able to sort of do this very quickly in memory if your index documents are really small. So we use this technique, sadly, on RavenDB to count millions of things, and that uses Lucene under the hood, and that worked really well. And we're getting this set up on Cassandra and production today, actually. So I'm excited about it. But yeah, in development, it's worked great. So that's how we do that. Any other questions? Yes. How do I deal with wide rows? In Solar? In Cassandra. Okay, let's say the answer is with Solar, you don't. You're supposed to run away screaming from wide rows if you're using Solar indexing. With Cassandra with wide rows, it's pretty straightforward. We basically know exactly what column we want to start with, and we just grab the slice that we need. So we never have a query really where we're trying to grab an unbounded number of rows from a column family that we know has wide rows in it. We try to sort of cap everything if we can. Good question though.